Good day everyone, and welcome to the Solve and Evolve series of lectures on linear dynamical systems. Today is our third lecture, and as we planned, I'll be talking about the equilibrium points of the system today, and I'll be considering an autonomous system and will take its center as the equilibrium point. If you remember, we talked in the previous lecture that it is sufficient to establish and analyze an autonomous system because every non-autonomous system can always be converted into an autonomous system. So we'll together determine the nature of the equilibrium points and the direction of flow of the system about the equilibrium points based on their eigenvalues. So bear with me. And now I want you to look at some visuals and develop some ideas about the motions of the systems shown in the visuals. For example, in the first one, you can see a black hole. That image is taken by NASA, and the black hole shows some spiral movement that is centered towards the center, and it looks like all the matter that is shown in the spirals is falling into the hole, and that's exactly what the black hole is. Any dynamical system may which could be of light, of sound, or radiation, or whatever that revolves, that is moving close to the black hole, has to fall into the hole due to its extremely high gravity. So the purpose here to understand the direction of motion of all the matter around the black hole that looks like a spiral and is directed towards the center. In the second visual, you can see some rings, and no matter what the direction is, it looks like they are all circular rings, and any motion around the center is in circular motion. In the third visual, you see some central points Q1 and Q2. Of course, they represent an electric charge, and there are some motions of the electric current that is shown around these electric charges. The important thing here is to see that everything is moving away from the charge, from the arrows shown. And in the last visual, you can again see some spirals, but this is different from what you observed in the black hole because now the spirals are moving away from the center. All these visuals are contributed by the dynamical systems that represent these orbits, and the nature of these orbits is determined completely mathematically by the dynamical system itself, and that's what I'm going to talk about today, and see how a dynamical system and its specific features tell you how to determine the direction of motion towards or away from the center in terms of the eigenvalues of the dynamical system. And here we see the graphical representation of some of these motions. In the first case, we see that the trajectories are forming circular orbits. In the second case, we see that the trajectories are moving away from a center. In the third case, there are again circular motions, but in 3 dimensions. And the fourth case, we see the center has the trajectories moving away from it in different directions. So we need to analyze the system itself to see how these solutions can be obtained. And now we get back to our original dynamical system, which we represent in the matrix form dx dt equals ax, where A is the representative matrix of the dynamical system in terms of the coefficients of variables. We know that the equilibrium point of the system would be the center, the origin if A is non-singular, which means that the determinant of A must not be 0. It's not hard to solve equation 1. We know that it's separable and it can be solved as you see in the visual. Please note that the vectors are represented by a short underline under them. So the vector x, since it's not a scalar, it is represented within underlined so that to differentiate from a scalar. And once we establish that the solution of the system is in the exponential form, e to the at, we can write down the general form of the solution that we know as e to the at times the eigenvector v of the matrix A. And if we just recall some information from our first year mathematics, in which we studied a Taylor series expansion, or in particular the Maclaurin series, where the Taylor series is expanded about the point 0, then we know that any exponential function can be expanded as a summation of the exponentials of e divided by a factorial. In another important and a beautiful idea from this that we can deduce is that the exponentials of two matrices A and B commute if the matrices A and B themselves commute, because we know that in general matrices may or may not commute, but if they commute, then their exponentials also commute. And there's a very simple proof associated with this, which we'll see in the next slide. So we see that the product e to the a, e to the b commute with e to the b, e to the a, because the product ab commute with ba. And we apply this simply by taking the expressions for k equal to 2, just to make it simpler. And when you multiply, you will see that there are some factors having the products ab, which you can replace with ba. And then the expressions will remain the same. And to verify that, you can actually perform the product e to the b times e to the a, and then see that you will get the same expressions. So let's talk about the eigenvalues of the dynamical system. And by the eigenvalues of a linear dynamical system, we mean the eigenvalues of the matrix A associated with the system. You might have studied that before, how to obtain the eigenvalues of a system A. If you haven't, then I will give you a brief description, but I expect that you have studied that before coming to this course. Okay, now by definition, any real number lambda and a vector v that is associated with the matrix A can be linked by the eigenvalue equation given as A times V equals lambda V. Yes, this is called the eigenvalue equation. And this equation says that when we multiply a matrix A with a vector V that is associated with it, then the association is that the multiplication of A in V results in increasing or decreasing the length of V instead of rotation. And that increase or decrease depends on whether lambda is positive or negative. So AV equals lambda V is the key to determine if lambda is an eigenvalue and V is an eigenvector of A. And in that case, the solution would be described as x equals e to the lambda t times V, which is a particular solution in which we have taken all the arbitrary constants as 1. Otherwise, in the general solution that is represented by equation 3, you can see that this summation can be expanded as C1 e to the lambda 1 t times V1 plus C2 when e to the lambda 2 t is multiplied with V2, and so on to any number of eigenvalues and eigenvectors. The only important thing to consider is that each term has lambda 1 corresponding to vector V1, lambda 2 corresponding to vector V2. So we cannot exchange eigenvalues and eigenvectors. We have to keep the eigenvalues with their respective eigenvectors. Now let's consider some more ideas about eigenvalues and eigenvectors of a dynamical system. And since we know that the system is represented by the matrix A associated with it, so we will consider the eigenvalues and eigenvectors of the matrix A. So if A is an n by n matrix and it has lambda 1, lambda 2 up to lambda n as distinct eigenvalues, mind my words, so they should be distinct eigenvalues, then the associated eigenvectors v1, v2 up to vn will all be linearly independent. So it is very important. But the problem is that if we are dealing with a higher dimensional system, then it is not easy to determine if all the vectors, eigenvectors, are linearly independent. So we consider a simpler case, as we have been doing from the beginning, that we are considering with two-dimensional dynamical systems to understand how the independent eigenvectors work to understand the equilibrium point and its nature. So we are considering the solution x for two independent eigenvalues lambda 1, lambda 2, and independent eigenvectors v1, v2. And we know that lambda 1 plus lambda 2, the sum of the eigenvalues, must be equal to the trace of A in that case, and the product of the eigenvectors lambda 1, lambda 2 would be equal to the determinant of A. This is high school mathematics, if you can recall it, and it's not a very hard thing to recall. The characteristic equation, therefore, would be the equation that always corresponds to a quadratic equation and would be of the form p of lambda, a polynomial in lambda, which is lambda squared minus lambda times trace of A, and the last term would be determinant of A. And p of lambda should be equal to 0 for the characteristic equation of a two-dimensional system that we deal with. And now you may have this question in mind: how a quadratic equation in lambda help us identify the classification of the equilibrium points of a dynamical system? And a very straightforward answer is the Cayley-Hamilton theorem, which says that if lambda is an associated eigenvalue of a matrix A, then having a characteristic equation in lambda is the same as having a characteristic equation in the matrix A, taking A as the variable of the polynomial. So for the polynomial in A, we can describe it as A squared minus A times trace of A plus I times determinant of A. And please note that we have used the matrix I, which is the identity matrix, in the third term to convert this term into a matrix, as all other terms are matrices, while determinant of A itself is a scalar. So to have a monotonous equation in matrices, we have to use the identity matrix and multiply it with determinant of A in the third term. And then expanding the polynomial, we see that it comes out to be a perfect square of A minus lambda I. And now you can see that it actually is the same equation, is the same representation of the eigenvalue equation AV equals lambda V that you have seen before. Or we can also write it as A minus lambda I times V equal to the zero matrix. So both of these equations represent the same thing, and they are representing the same information as represented by equation 4 in lambda. So equation 4 is the key. And we can rewrite that into a polynomial of the form lambda minus lambda 1 times lambda minus lambda 2, as it is the quadratic equation in lambda. Three cases arise to solve it. In one case, both of the eigenvalues can be negative. In the other case, they both can be positive. And in the third case, one of them can be positive and the other could be negative. We consider all these three cases to classify the equilibrium point of our dynamical system that we are considering. So we consider the cases where lambda 1 and lambda 2 are real and they have two linearly independent eigenvectors, even if they are equal. The solution itself has two terms of the form e to the lambda 1t times v1 and e to the lambda 2t times v2 with both positive and negative signs, and that determines four semi-infinite straight orbits. Now, from these terms, we notice that the sign of lambda 1 and lambda 2 will determine where x1 and x2 approach to 0 or infinity. So if lambda 1 and lambda 2 are less than 0, then the orbits will approach towards the equilibrium point. And if they are greater than 0, then the orbit will approach away from the equilibrium point. This is just mathematical interpretation. Now, the qualitative behavior of orbits will be obtained by understanding the eigenvalue equation AV equals lambda V, because A times V means rotating the vector v, while lambda times v means stretching the vector v. So this rotating and stretching, when they combine, then they give us an eigenvector. And in this way, we can have the qualitative solution of our system in the form of the canonical form dy dt equals gy, where G would be the matrix of the eigenvectors, and the corresponding matrix of eigenvalues B would be lambda 1, 0, 2, 0, lambda 2, where lambda 1 and lambda 2 are distinct, and lambda 2 will be replaced with lambda 1, with the second component of B replacing 0 with 1 if lambda 1 equals lambda 2. And now we see this example, which is dx dt equals ax, where a is defined by the components -3, 4, -1, 1. You can easily find the eigenvalues of a by the eigenvalue equation, and it is seen that they come out to be -1 and repeated with a single non-zero vector 2, 1. Now the solution we have talked about that in this case would be e to the 2t times I plus t times a minus 2i times v, and we can see that each component of the solution is the negative power of e, which clearly tells that as t approaches to infinity, the solution will approach to 0, which is your equilibrium point. So this equilibrium point with repeated eigenvalues is quite attractive, and all the orbits will be attracting towards the equilibrium point. We will see that after a few slides when we draw the phase portraits. We know that quadratic equations may have complex eigenvalues. So in this case, if our characteristic equation in lambda has complex eigenvalues lambda 1 and lambda 2, then it's easy to understand that lambda 1 and lambda 2 will be complex conjugates of each other, and their corresponding eigenvectors will also be complex conjugates of each other. So in this case, we don't need to express the solution in the same form as we expressed for real eigenvalues, but we just have to separate the solution into real and imaginary parts. As you can see on the board, that it will be C1 times the real part of e to the lambda 1 TV and C2 times imaginary of e to the lambda 1 TV. We don't need to express the components in lambda 2 and V2, because lambda 2 will be a complex conjugate of lambda 1 and V2 will be a complex conjugate of V1. We don't need to express both parts, both complex conjugates in the same solution, as they represent basically the same thing, just in the opposite direction. Okay. Now the canonical form is also easy to obtain in this case, because the principle remains the same, that y would be G inverse of x, where G would be the matrix of the real and imaginary parts of the eigenvectors, and B, our matrix of eigenvalues, will be having A and as the first and fourth component, where A is the real part of lambda, as you can see, and B, which is the imaginary part of lambda, will occupy the spaces second and third in the matrix, except that the third component would be negative. And there we have an example of x1 dot, which is actually dx by dt. So the first equation is dx1 by dt equals x1 plus x2, and the second equation is dx2 by dt equals minus 2x1 minus x2. You will often see such expression in replacement with x and y. You will have x1 and x2. So you can extract the matrix A as 1, 1, minus 2, 1, and the characteristic equation would give you the eigenvalues lambda equals I and minus I, but since we have clearly talked about the eigenvalues that one of them would be the complex conjugate of the other, we don't need to take both of them, we will take only one. So it's okay to write lambda equals I. And so our matrix B would be having the real part as 0 and imaginary part as 1. So we have expressed it as A, B minus B, A. And the matrix G would be the matrix of eigenvectors, which are again the real and imaginary parts of the eigenvector v, and assuming the arbitrary constants to be equal to 1 for the sake of simplicity, we can express the real and imaginary parts as components of x, and that turn out to be minus cos t and cos t plus sine t. And this will be obviously the first component, x1 as minus cos t, and x2 would be cos t plus sine t. Correspondingly, we obtain y as g inverse of x, as you can see, and also the components x1, x2 and y1, y2 yield two equations with us, which is y1 squared plus y2 squared equal to 2. You can easily verify that from their components. And x1 squared plus x1 plus x2 whole squared equal to 1. Now, both of these equations represent the right-hand sides equal to constants, so they represent the first integrals of the system in both the original and the canonical form, and they represent circular orbits. And the real canonical form therefore yields the second derivative of y1 equals minus y1, which means that y1 double dot plus y1 would be equal to 0, which represents the famous simple harmonic oscillator. We also name equilibrium points differently depending on their nature. So in the first case, where the eigenvalues are real, distinct, and negative, the nature of the equilibrium point is that the orbits are attracted towards the center because of the negative exponents of the exponential function, and so they are called stable nodes. The unstable nodes would be when the eigenvalues are real, distinct, and positive, and due to the positive exponents of the exponential function e, we have all the orbits tending to infinity as t tends to infinity, and which means that the orbits will point always away from the equilibrium point. So here's a different view of another system, so you can understand how different views represent the same thing. For stable or unstable stars, the eigenvalues must be real and repeated, and we are considering the example 1 that we considered before, which we solved, and we found the eigenvalues to be minus 1 and repeated, and so all the orbits must be pointing towards the equilibrium point, and in this case this will be a stable star. You can see two different views of the system concerned. And now we are looking at stable and unstable nodes where the eigenvalues are real and of opposite signs. So lambda 2, for example, is less than 0 and lambda 1 is bigger than 0. And in this case, you can see that one of the component would approach to 0 as t tends to infinity, and the other will be approaching away from the center. So you can see all these types of nodes which are the settled and unstable all in the same diagram with the phase portrait of the system that is mentioned to you as dx1 by dt as x1 minus 3x2 and dx2 by dt as minus 3x1 plus x2. Much all about today's lecture. I hope you enjoyed it. Please remember that this was only an introductory micro course in linear dynamical systems, and the purpose of this course was to equip you with the preliminary knowledge that you would need to study dynamical systems at your institution if you are entering or are doing a science or engineering program. My next videos will present some more examples for your practice and understanding, and I will then move on to the new topic, which is about partial derivatives and error estimates. This is also a very interesting topic, and you will be definitely enjoying it if you are a math savvy.